Hi, everyone. Thank you for joining us today. My name is Natalie C. We are here for Sketchulation tutorial part 6 for new users. I'm actually calling here from Canada today. Hopefully my audio is okay. I'm in my in-laws house in Toronto area. And joining us is Mike. As you guys know, Mike is one of the principals at Tipping, and he's the developer for Sketchulation. Today, we're going to be covering 2D structural analysis for 3 different examples, concrete beam analysis, and we're going to be talking a little bit about creep and how to review the results associated with concrete beams. And then we're going to do another example for concrete footing with soil springs. I know this is really important for all of us. Soil springs, of course, bring a lot of challenges if you aren't able to manipulate those in your software. And then finally, retaining wall. But before we jump into part 6 tutorial, we're going to do a little quick review of part 5 tutorial. Actually, it's specific to 5A or 5, yeah. So I'm going to hand over the mic to Mike.
All right, thank you, Natalie. Sorry, I just wasn't quite prepared.
And just a quick reminder, Mike, can you turn on your keyboard
Yes,
view for Sketchulation? Thanks.
will do. Okay. Turn on the keyboard monitor. Okay. And slide this over, share my screen. There we go. Okay. So last time we talked about graphing, and we went through a couple of examples of graphing. We created a little calculation here, a table where we were estimating the deflection of a wood shear wall, and accounting for the different components of the deflection. So these are the equations from the NDS for the different components: anchorage, bending, shear. I'm sorry, this is going to be like just a slip for the actual anchor, but then this is the deflection due to the anchor. So we have these 3 components of deflection, and we just use this to generate a little bit of data. And then we showed that you could make a series in a chart by first creating the chart, CHT, and drawing it on here, and then typing series, CR, to add series. And we showed that there are a couple of different types of series. I think I actually showed an expressions series to start with. So we created a little parametric expression and showed that. And in this particular case, we have a table columns type of series. And so we select this table with our data, table 2, and on the x-axis, we would have the number of stories. And then in the y-axis, we would include the deflections for our 3 different components, like that. And then those would be in multiple series, and we would click add, and then this would generate our data, and then we show, or the graphs rather, and then we showed that you could once we have that, you can manipulate the graphs. I typed EDS edit series to bring up these things, and then we want to make this histograms, so we can go into the sidebar editor and set these as histograms, and then lastly, we wanted to stack the categories. So this is a property of the chart. The chart has many different properties, but within the general tab, we can stack the categories like that. And that's essentially what we did. And then we just showed that you could manipulate the graphics, what's showing with the axes, say axis X, we don't want to, or say axis Y, we didn't want to see everything. So we just turn off, say, the major grid lines and the ticks. Well, we keep those, and we'll keep the labels, get rid of the minor grid lines. So we can, well, I kind of have it flipped, but you get the idea. We can adjust the visibility of our graph, and we can put in a title by double clicking, deflection here, like that, and then we click out of that. And we walked through these sorts of options. And then we went into using a pie graph. So we created another table here that was basically just looking up the data from our first table to summarize it. And then we showed that you could make a new pie chart, PIE, and we draw the pie chart. And it has no data to start with. And what we want to do is create a data array for it to read. And so we use the table columns or TableCols function to read the table with our data and then create an array that the pie chart can read. And we talked about how you can use this function to basically read the any set of data from a table and render it as an array. You can manipulate it that way. So we're getting the columns component and delta and hue from this table one here, and I described how you can create a hue column that will change the colors of your pie, the wedges of your pie. So I bring up the sidebar editor and I reference the variable that's holding my pie chart data, and then the pie chart reads it and comes up with the pie wedges. And then you can change various things, options with the visibility of the pie chart in the sidebar editor. And then we went on and we showed a more complicated graph with more data. We have this data table that has ground motion, interstory drift values for 11 different earthquakes for several different nodes on each floor, and many stories tall this building is. So we had several locations that we exported from a different program. Location 1, 2, and 3 defined by these coordinates, and then we created this formula here to be able to identify which location is which using a query, the query function. And then we had to organize our data, sort of categorize it. We had to know that what we imported in order to do this. So this was a bit of a tedious thing. We showed how you can make data or make values in the table. You can pull them down like you do in Excel and have them repeat. And we showed how you can count cells. If I push Shift Control down and then I push F4, it counts the number of cells that I selected, and then I can put that number in the clipboard. And then if I have two sets of data here, then I would just take this would be data set 1 and data set 2. I push F9 to duplicate, and in this case, it already put in what I had counted from before from the clipboard, and in this case, I divide it by 2 because I have 2 components of data here, and I click OK, and it does this duplication of those values. So we showed that just so that we could illustrate how even though you have to do a bunch of handwork in here, there are lots of tools to be able to copy things and duplicate things on within the cells of the table to make light work of that kind of thing. But the whole point of that was to then show that we could create a graph. So again, we make a chart, CHT, we pull that over here, and then we type SCR to make a series. And again, this is going to be a table column series, and we're referring to that table drift 1, like that. And then the X data would be, let's say I want to plot all the earthquakes, CQ1, so multiple all the way through 11. And I'm going to put all these in one single series. And then the vertical coordinate will be my y-axis. I click OK, and I get all these lines and everything all over the place. And really, I don't want to see all those lines. I just want those to be markers. So I go in here, EDS to edit the series, and I just turn off the line. So now I just have markers. And then let's say I also want to plot the average, which is over here in my column. I might not have mentioned this, but there's an average function, and then there is a colon operator within tables where you can basically get an array of values using that colon operator. So it's going to take an array of values from the column named EQ1 to the column named EQ11. So I have these average values here, and I'll want to plot those. And I also notice I have positive and negative data, so that envelope will be 0 or 1. So when I make this, I'll do two different series here. And I showed that we want to plot the average value here. We still want the vertical coordinate to be our y-axis. But now we're going to plot our positive and negative separately. Oh, one thing I also forgot to mention here. We wanted to filter out the displacement. So in this data, we had response was 0, was drift, and then there's a whole other section of the table that's displacement. So I have displacement values and drift values in the same table. And so that's problematic in most circumstances, like in Excel, you'd have to rearrange things in order to deal with this. But in Sketchulation, you just put in a filter. So I double click on that series and I put in a filter so that I'm only pulling out the data that's representing interstory drift. So I would say RESP equals question mark. So that's the a Boolean operator to tell whether something is equal to something else as opposed to an assignment operator. And we want that to be 0. And now we see our numbers got a lot lower. Now they look like drifts instead of displacements. Okay, and then I wanted to go back and plot the average values. And in here, that's still set up the way I had it before. But now what I want to do here is I want to put in, again, the RESP is equal to drift. So that's RESP equals 0. And now we want the envelope, ENV. Again, that's a table, that's a column in my table. We want that to be 0. So that's going to be the negative data. And then I can copy that and quickly add both the positive and the negative data at one time. So this is going to make 2 series here. And they're by default, they're not showing the lines because the last series didn't have any lines. And now I want to go ahead and make those things show their lines like that. Oh, and then I see I have all these, still a lot of dots on every floor. And why is that? Well, the reason is because I have several locations on every floor. So I could filter my data here again. I could add another piece to this filter to say to plot at a certain location. So I could say loc, capital loc equals question mark 1. And so now that is just going to plot values from location 1. That would clean up some of the data. You can see the orange lines on the positive side. Expected the orange lines on the positive side to become less, like that. And it still seems like, oh, and of course I have multiple directions and a couple other things going on. So what we want to do though is we don't really care about all of these things. What we can do instead of adding more filter pieces to this, we can just delete that location 1, although I could plot by location, but I might just want the maximum. I don't really care about which location it is. So in that case, I would use this disambiguator. I would say sort by ascending y, and then I would just take the maximum absolute value. And so that boils all those locations in both directions down into one set of averages. The dots are still showing all of the values from any location, any value, so that can be a little confusing sometimes. But we're going to show that spread of data that way. And then lastly, just a quick, there's lots of different ways to change the appearance of things in a macro way. So for our averages, I would click this embolden button here and right click and set this to be lighter. And so that's kind of looking a little nicer. And then lastly, I want them all to be the same hue. So I select them and I click the H button here. And let's say I feel like a purple day. So that's going to be purple for us today. And what's nice about that is it doesn't change the lightness of the series. It just changes the hues. So you can edit just certain components of the color. So that was a very quick primer on some more graphing, and we're going to do more on graphing because there's still lots to be done on that. But I'm going to leave that now to jump into today's topic. But before I do that, I'll just see if anybody has any questions.
Mike, can you demonstrate for the bar graph how you show the point labels?
Oh yes. So any graph, if I type, well, I already have the series editor open. So any graph has the ability to put point labels on it. And there's a pretty robust set of things you can do with tagging and stuff to get complicated, get data out of the table and have it display. So I click the help button next to the point labels text box there, and then you can get more information on that later. But let's say I want to display the Y value at each point. I put in supposed to be lowercase y, and then I just click away, and you see it's displaying the Y value for each one of these. Now, one thing to notice here is the value that it's displaying is not the stacked value. So that's a little bit of a subtlety with the stacking. This is going to be the actual value from the series. It's a little bit confusing. I should probably address that. But for example, if I just go back and I unstack the bars, you'll see what I'm saying, that these are now the values of 0.58, 0.64 are the values from the table. And you can also do other things with point labels. You could add text, like I could put in a quote to say that that's inches, or I could put in maybe like this comes from a table columns type series. So I could also display some other piece of information from that table. So for example, I could say use the call. This is a special one here, the call tag. And let's say I want to display H for some reason. So it's going to display the value from column H next to my the other things that I've typed in there.
Right. And before we start the next tutorial, I think Abdul had a question for you about text and how to, when you change Annoscales. I don't know if you wanted.
Yeah, let me just show that quickly. So if you have to change Annoscale for some reason, something's not fitting and you want to adjust something, there's a couple things that you want to know. First of all, let's say I have to change this to 200. When I change this to 200, the page size is going to grow and the texts are all going to get bigger everywhere. So the chart text is going to get bigger, the expression texts are all going to get bigger. And the reason for this is that now our page is effectively bigger, but the text needs to appear the same size on the paper, and that's controlled by the text style sidebar. So a lot of these things are in the body text style, and so that needs to come out 9.75 points based on what we've entered here, and we can change that if we like. But if you think about it for a second, because the paper got bigger, the text has to grow in order to have the same size on paper. And so right away, if I have this situation, what I would do is I know what I just changed the annotation scale to. So I would just select everything in my layout and use the scale command SC like this and snap to some place that makes sense. And I would put in the ratio of the annotation scales, 200 over 100. And then everything goes back to looking correct, like relative to one another. But it's now a larger annotation scale. So, and then of course my block, I have to look at why my block is not scaling up with it. And then another thing to know about is if, let's say let's say that wasn't the issue. Let's say we were just moving some things around and things just got mixed up, like the expressions were all messy and not aligned, and we were just trying to clean up things. So there's a couple commands here that you want to know about. You select everything and you start to type SPC space annotations. This works for expressions, but it also works for text objects, and it works for images and I think even charts. A number of things will kind of align themselves with using that command. And there's a similar command, SPCH, so that'll space these things horizontally if that's what you prefer to do.
That's great. If we have a bunch of expressions and there's a text that follows each one of these, and you want to align the grips, can you demonstrate the align function?
Yeah. So a couple other things here then. If I select like this, You see all these orange dots, those grips are selected. That blue dot is not selected, so it's not part of the grip selection set. You can also see that on the bottom left. It says 10 entities, 9 grips selected. And then I would run the align command, AL. And this works in this context, it works for it's going to work on any grip that is selected. So I happen to have these selected, and it's asking, now I can select a boundary to align the grips to. Like if I had a line that was there that I wanted to align to, I could select that, or I can just push enter. And now it's asking me to create a line boundary. And let's say I just draw a straight up line like this. It doesn't have to extend beyond where all the grips are. It's going to move these things perpendicular to the line that I draw like that.
Great. Abdul, did that answer your question?
Yeah, thank you.
Okay, great. Thanks, Mike.
Okay, great. You're welcome. So now let's get into today's topic. I'm going to start with, well, we're going to make a simple concrete beam. And with this, it's going to be a very simple example, but with this example, I just wanted to show the features in Sketchulation for creep and shrinkage that we have in concrete. So what we would do is I've made a new worksheet, and we're going to draw a new frame element. Let's say this frame element spanning 25 feet, like that. It's going to be a concrete beam, and I'm going to make some restraints at the ends, like this. And then I'm going to just put in a simple line load, LDL, like this. And then that'll be my dead load, and then I'll make a new one. Select the grip C, that becomes my live load, and then I'll just make some things up here for my loading. So let's say my W dead is 200 PSF. It's a heavy system, and my W live let's say is 50 PSF for an office, and so then the WD, let's say my trib is like 10 feet or something. Oops, I'm gonna make that my B, my trib, like that, and then WD is equal to B times W dead, and WL is equal to B times W live. So I have these loads in here like that. And then this is gonna be my dead load, so I select this, I put in WD, like that, and it's gonna be my live load, WL, like that. Okay, so I'm good to go on those things. And then now I want to create my load sets. So LS, we will use the wand. We're not gonna mess around with anything custom here. And I'm just gonna use all the dead and live load combinations, both LRFD and ASD, like that. I click OK. So now I have my load set here. I assign that to the dead, enter, and then I assign this one to the live, enter, just double check. Looks good. Okay, so now I have my simple beams set up. Now I'm gonna make the cross section. I'm gonna totally guess at what cross section worked for this. Now you'll notice that this is annotation scale 100. This is good for looking at the beam and elevation. But if let's say this beam needs to be a 12 by 24, that might be the right number for this. If I start to type that, I'm gonna do a concrete beam. And yeah, I'll start with 4 number 9s to start with and see what that looks like. And I'm gonna put at 12, 24, like that. You see, it's very small. And that's because we know this when we draft, we wouldn't put a beam elevation on the same annotation scale as its cross section. So what we want to do actually is create a new layout where we'll draw our cross sections, and it'll be a separate layout from where we're doing this other calculation here. So I'll make a new layout. I usually call it cross section, or you could name it the annotation scale number, whatever you like. And I'll go back here and I'll control X on that, and then go over to my cross section. I always like to make a page just to have one like that, and then control V. It's small because my annotation scale is small. We normally put these things maybe 16 3/4 inch scale, I got to get rid of that block thing. I haven't looked at sort of a new feature using the page block, and so it's not scaling properly. Got to look into it. But here's how this is how my cross section is going to look on the page once I put it into the other layout. That looks pretty good. I like that size, so I'm happy with this annotation scale. Now I'm going to go ahead and define this cross section's properties. So here's where I'll bring up the fiber material editor, command FM, and I'll make a new concrete. I'm just going to use 4 KSI for now. Should be fine for my demonstration. And then I got to make a new mild steel, 60 KSI, should be good. And then I use the paintbrush to apply to the outline of my concrete, and then the rebar here, like that. And then I double check the colors. Okay, that all looks good. Now, when I made the concrete, you can graph the backbone curve for the concrete, and you'll see there's 2 graphs. There's the one, the solid one is the sort of the default values that we would normally have if we're looking at doing a strength calculation in ACI, and then this dashed one. And the dashed one is accounting for creep. So there are a bunch of options down at the bottom that you only ever look at if you're trying to do an estimate of deflection, long-term deflection. And so these creep values are going to come, there's documentation here that we've included. It's going to bring up the PDF program here. And you can change some of those options if you want, but you can also just look up how the values are being used in case you're curious. You don't necessarily need to do any of this, but you can look at it if you're interested. But these are the values that are inputs for the calculation, and the defaults are usually pretty good. And what they lead to is a graph that looks like this. So when we do our analysis, the concrete's going to follow this dashed line for our long-term deflection calculation here. Okay. So those are assigned. I double check the colors, and I have a cross section. Now I just need to tag it. I use my shortcut command TG, and I call this thing my XS cross section, like that. So now it's tagged, and I can take a look at the moment rotation curve if I'm interested in that. I'm just going to see what is my peak moment capacity. It's 2,000 kip inches. I think that's going to be way too little for my beam design, but we'll see in a second here. And then now I'll create the frame element type that I can assign to my beam on the other layout. So FET, I click new, and I go to the ACI type of design. And here it's asking me for the boundary entity right here. And that's going to be a symbol pointing to my cross section. So I entered that there, and you see it meshed the cross section for me. There are some other options here that you'd want to look at too for shear capacity, for example. And then what we also will pay attention to is this nonlinear section analysis versus using an I effective over I gross. So if you're not aware in concrete, you're supposed to, if you're trying to calculate deflections, you would normally use an elastic analysis, and you would put in a crack factor. And that crack factor is going to soften the beam. So you might use, say, 0.3 EI gross in order to estimate the effect of cracking and creep. So you can do that in here just by putting in a number directly. If you put in 0, I cracked is used, which means that you can go back and look in your textbook about what I cracked is, but it essentially takes the cracked moment of inertia of the beam, but it's typically about between 0 and 0.3, something like that. And again, you can do a nonlinear section analysis, which would mean it's going to actually use this fiber section for the analysis. And if we do that, then we have the option to include long-term creep. And clicking that button is what is going to control what concrete material is used for the analysis. So for example, I'll make this cross-section here my excess without using the long-term creep to start with. I'm going to make a viewport of this, and I'll put that on my calculation on the other page. So VP viewport, draw a box around it. So now when I move this viewport away, you can see it's just looking, it's a viewport looking at this area over here. So then I want to Control X, go to the previous layout, and I put it on here. Now to start with, that cross section is going to be too small because it was drawn on an annotation scale of 16, and this is an annotation scale of 100. So I want to scale that up, SC, by 100 divided by 16. And now my cross section is to scale on this page. I could also put like a little title block with those are built into Sketchulation for that. And then let's say also I don't want to see the boundary, so I would oops, what is that called? Draw a boundary or something, draw outline. Yeah, I'm going to turn that off. So now you can't really tell that the cross section is drawn on a different layout. Okay, so now I want to assign this cross section to my beam. So I'll bring up the modified properties sidebar here. And in the element model dropdown, I pick XS. And if I want, I can display the label that will remind me what I've chosen. And I can't remember where it is, so I'll start to type this. Geometry, there we go. Element model. Okay, so that shows what the assignment for that beam is. And I should be ready to run my analysis at this point. So I type F5, and I can see, oh, here's my deflection, 1.19 inches. Now I can move this over because I'm gonna do my other command here to do the viewport model, VPN. And this is the way that we plot lots of results all on the same page. Draw a box around my model. And I want to show my DCRs, my moment, my shear, maybe dead plus live deflection like that. And then we should be good to go on that. I click this down, push enter. And so now we see what we have. Hey, my DCR is over 1, so it's not great, but it's not terrible. Well, I mean, it's not nearly good, but it's within range. I can add some reinforcement probably and get this thing to work. And we notice our deflection here is 1.44 inches. Our length of beam is 25 feet. So if I put a little calculation here, 1.44 inches, 25 feet divided by 1.44 inches. This is L over 208. This is for dead plus live, so code wants me to keep that under 240. So I'm not quite there yet. I could have done this lookup with the LRes functions, but I just was being expedient about it. So anyway, my beam's not working yet, so I need to go back and let's just try to get this thing to work. I'll double click on the viewport. And it takes me right to my cross section, and I just double check. What do I have? What are my options here? Modified properties. What size bar? I have 9s. So maybe I'll start with just copying another couple of 9 bars, and maybe I'll make that 4 number 9 bars. And of course, my ties are going to have some trouble, but we'll let the contractor figure that out. And then I go back to my cross section. Nothing is analyzed. I have to push F5 again to reanalyze. And now our beam is working, and our deflection is now 0.82 inches. Like that. Check that. And so now my deflection is doing okay. And we might be inclined to think that that's good, that I've got a design that works. The problem is that we've assumed in our frame element type, we've assumed a certain value for I. So if I go into the frame element type sidebar and I pull down this thing that says description, I can see what it's using. It's the I gross for that cross section is 18,660, and it's I cracked 8455. That looks like about half, right? 8455 divided by 18660. 0.45 I gross. So the question is whether or not that's realistic. Is that how the cross section will really behave? And so if we're not, if we really want a long-term deflection check, we should really go back into here and use the nonlinear analysis option and include long-term creep. And then when we rerun the analysis, usually takes a longer time. This is not bad for a simple beam, but it usually takes a little bit longer time, and we get a lot more deflection. You see that 2.1 inches in this analysis. 0.4. So now all of a sudden our beam is not working based on long-term creep, and so we really want to pay attention to that and take it into account. There's another issue that I want to point out that most people will not notice. You see this 66 kips, 66.2 kips. What's happening here is that the beam is growing and the cross section is responding with an axial reaction. So it's basically having to react to the cross section, trying to elongate. When a beam bends, if we look at this, let's go back into the viewport. And I type MR. At our nominal moment, you'll notice that the only portion of the cross section that is in compression is up here. It's just about maybe a fifth or something of the total cross section, and the rest of it is cracking. So if we look at what's happening at the neutral or at the axis of the member, we get a strain in that material right there at the axis. I think I even report it here. Strain at axis 0023. So what that says is that the cross section is in tension by a factor of 0023. That 0023 multiplied by 25 feet is going to come up like 0023 times 25 times 12. That's 0.7 inches of axial extension when you integrate it over the whole beam, if everything was at the nominal moment. So that's an overestimate. But that additional movement outward has to be taken into account by our analytical model. And so that's why these reactions are showing up the way that they are. You could see this also if instead of looking at shear force, we plotted axial force, 71.8 kips. Now, if we change this to a roller, so that it's not restrained in the X direction, now we get slightly more deflection, 2.16 instead of 2.14. But you'll see there's no more axial demand anymore. And I'm not seeing my, oh, I know what happened, or I think I know what happened. Let's see what's going on with my analysis cases. DCR. I wonder if everything's, not everything is converging. So I had a couple of issues with this cross section not converging, and I would try to figure out what's going on with that. Failed to converge for initial loading. So I have this couple of the load combinations are not converging, and so that's why it's not giving me a DCR, because if one of the things is not converging, then it won't give you the envelope of your results. We could go back into this and investigate further. What's the convergence issue? We know that part of it at least is due to the this extension because we put in the roller there. But this is gonna require basically just more effort to sort of figure out why it's having trouble with that part of the analysis. There are we can see that the dead plus live did converge, so we could look at the moment due to dead plus live like this. And look at it that way. The issue, though, I think you'll notice here that we have in these cases, like with live load, they first start with the dead load, and then they apply the live load separately because the live load is using a different concrete material. So this is the issue with creep, is that the material changes from one analysis to another, and so it creates some added convergence difficulties. But going back to this and just again, I'd have to work on my cross section more to get this all to work. But the basic idea is there. So, any questions on the concrete section analysis with creep?
Great.
Okay. Now I wanted to show quickly show the distributed soil spring component of the analysis. So if you go up into the examples, there is an example of a foundation footing with a point load. And that's what basically that's what this is here. So all that we've done here is we've put a point load with the dead and live, and we have our beam, kind of like we did in the other example. This is our beam here, tagged with it's double tagged actually. So this thing is free type MO. It's tagged as beam, but its cross section is the FTG footing. So we have two tags in this document. One tag is referencing the footing cross section, and the other tag is referencing the beam. But we can display the label. Now I remember where that is here. So there's our element model, and if I do that, you can see both the tag and its element model with a comma between them. So we have this dead and live load, and you'll notice here we have this spring. So this is very easy to put into your model. Let's say you might. I don't even know how you would do this without Sketchulation. It's not too easy actually. To start with, let's say you have your frame element, and it's in space. If we put in a restraint at the two ends and analyzed it, you would get a deflection diagram that looks like that. It's just supported at the two ends, and you have a lot of reaction at one end and a lot of reaction at the other end. But what you really want is something that represents a distributed spring. So in order to put that in, we start to type distributed restraint is what it's called. And we snap to the two ends here and here. And then we'll want to release these restraints. So first, might be inclined to just delete them. Okay, so I have no restraints, and I have my soil spring underneath here. And the units of the soil spring are in KSI. That is, you have the spring stiffness is basically kips per inch of length. So it's kips per inch is a stiffness per length of element gives you KSI. For example, here my footing width is B, defined as 3 feet. And you might get from your geotechnical engineer a spring constant of say 100 KCF for your analysis. And that comes out to 2 KSI. That's 2 kips per inch of length of beam. So that's how this gamma is defined. And so I can just double click into this and set this equal to gamma the same way that I would have done my linear loads. And so now I have a model that seems to be ready to run. I click F5, but it's not working. And so it says the model's invalid. And so I double click into that, and it says, oh, validating restraint entities, list invalid, none defined. And so the reason is because this model has no restraints in the X direction. It has restraints from the distributed restraint in the Y direction, but not in the X direction. So I type R for restraint and put this on there. And then the analysis runs right away. And we see that maybe this looks better than we had before, but you see it's not moving at the restraint. So what I need to do here is select that guy, type MO, and release it in the Y direction this time. So it's a roller in the Y direction. And now it analyzes, and now we're getting deflection that looks a lot more reasonable. From there, there's the analysis isn't the plotting of the results works the same way as other circumstances. We use the VPM command to create these graphs. But in this case, we might be interested in what's the soil pressure. So here I can see I have 20.6 KLF of footing load. That's in KLF, so kips per lineal foot, for my dead plus live envelope of load combinations. And I can get what that is in terms of KSF, because I know my footing width is 3 feet, so 20.6 KLF, I'm sorry, divided by 3 feet. So that gives me 6.9 kips per square foot. So I could do that by hand here, but I can also do that programmatically here, or using expressions by tagging the frame element like I did with tag BM, and then I use the elEnv function to recover the force. So F absolute, again, if you're not sure what these all of the options are in this list for results that you can return, you go up into hit F1 and start to type frame element, and you'll see the entire list here. And one of them, F abs, these should be alphabetical, maximum absolute load from a distributed restraint. So that's what we're interested in. And we type that in and we get that 20.6 KLF, which is the same number that we see on the graph. So that's good. And then we assign that to the value variable W soil, and then we divide it by B to get our stress in KSF. Then we can also, there's another function here where we can get the total load, 250 kips, total load from the entire distributed spring with this symbol here, tilde S. So now one thing you might notice here, I was noticing, it was kind of bugging me, is that there is some tension in our soil spring, minus 2.54 KLF. That's not what we want, because soil doesn't do that. So we can type ML, modify properties, and we can adjust our modifier. So it's a compression only type of spring. And then it quickly recalcs. What ended up happening is my KLF went up by a little bit, and then everything just updates like that. Okay, any questions on that example? No? Okay, I feel that we don't have enough time to do the retaining wall example, so I think we'll skip that one for today, and we'll come back to that at a later date.
Great.
Mike,
Yes.
can you model also the dip foundation? Let's say we have a pile that, can we analyze it here like this one with the passive active?
Yes. So, well, let me just show you where I was going with this. This was going to be the retaining wall example. I'll just show it as an illustration. Maybe we'll go through it in more depth later. But you can put soil springs or put springs wherever you like. So you could put in a spring as a passive. And that would give you could be a distributed spring, or you could put in a reaction with a spring value to maybe represent a pile. So that would be a distinct, any of these reactions, you can select them and give it a stiffness here. And of course you can put in, a horizontal spring. So if I wanted to do that here, I could put in something like this. And then this, of course, is pointing up and down to start with, but I want to set its angle, probably in geometry here. So by default, it's angled 90 degrees. We want that to be 0 degrees. You give it a stiffness, and then it will react in the same way, in a manner that's compatible with the deflections of the wall. Any other questions? Does that answer your question?
Yeah, thank you.
Great. Are there any other questions from the attendees today?
Right. Well, thank you all very much for attending, and do let us know if you have any questions that come to mind after the fact, and feel free. We have had some activity on the forum, so for those of you who don't know, you can click user forum in the help menu, and you can add a topic, add a feature request, report a bug. We do check that actively, so and we try to respond as quickly as we can. And with that, I would just thank you for your time, and hope you enjoy the rest of 2024.
Okay, that's the last tutorial for this year from us. So we'll see you guys in January. I hope everybody has a great holiday, and that you'll continue to enjoy Sketchulation with us.
Thank you.
Thank you. Thanks, Mike.